Today is March 19th, 2020, and we're going to go through, this is our first video on section 1.4, Euler's method. So I know it's been a while, but you might recall from Calculus 2 when we covered numerical methods for integration. Well, Euler's method is really similar to that. It's really similar to numerical methods for integration. And just like in Calc 2, when you did numerical methods for integration, you took this interval from like a to b. In this case, the book is doing interval from 0 to 1, or here it's a to b. And you break it up into equally spaced numbers. Like it used to be like x0 to xn, but whatever, now they're t0, t1, t2 to tn. And you break them up, and the h is the space in between them. So h is 1 over the number of steps you're doing. Okay, and so then that's h is the step size. And where in Calc 2, h would have been like the rectangle width. And so then you're basically determining where your next value will be based on sort of the tangent line from that graph. And so say we have this differential equation here, so you know that y prime is equal to this function. Then you can say, well, the slope of the tangent line is rise over run. So rise would be new value minus old value divided by run, which would be h. And so that's your rough approximation of the slope. And so that means that the next value is going to be roughly the old value plus slope is rise over run. So if you multiply times run, you get rise. So old value plus whatever is supposed to go up based on the slope. And that's the basic premise. And so then the book is using capital Y's for the numerical approximations, so that you're not confused by the actual y and the y that we're using to approximate it. And so then y0 is equal to whatever, capital Y0 is equal to little y0, but then capital Y1 is the old value plus h times whatever the differential equation is. And then y2 is the next value plus h times whatever the differential equation is, and so on and so forth. And so this is called Euler's method. And so here they go through the particular situation where they had t is 0.1, and you're using that like differential equation of it being like x plus t. And so then so then they kind of go through. Here's k is like what step you're on. So tk is there. And so this is your approximation. And then this is the actual value because they picked one that's actually solvable. And then this is your error. And then your percent error is right here. So let's do activity 1.4.1. So consider the initial value problem, y prime equals x plus xy. And then y of 0 equals 1. So first we're going to use separation of variables to solve this initial value problem. So let's do that first. So we're doing y prime equals x plus xy, and y of 0 equals 1. So then I've got dy over dx equals x times 1 plus y. So then dy over 1 plus y equals x dx. And so integrate both sides, and you get natural log absolute value of 1 plus y equals x squared over 2 plus c. E to the power of both sides gives us absolute value of 1 plus y equals e to the c that old trick that we're doing over and over and over again. So e to the c just is a new unknown constant. We'll call it c times e to the x squared over 2. And then this unknown quantity c could be positive or negative, so that can swallow up that absolute value, e to the x squared over 2, and then subtract the y. So y equals c times e to the x squared over 2 minus 1. Now, I know that y of 0 equals 1. So 1 equals c times e to the 0 squared over 2 minus 1. So that means 2 equals, and then e to the 0 is just 1, equals c. So that leaves me with y equals 2 times e to the x squared over 2 minus 1. Okay, so that's my actual solution. And for this activity, they gave us one that's solvable so that we can actually see our actual error. Even though the only way you really want to use this method is when you can't solve it. Okay, so we did that. So then let's compute. So now we're going to compute y of x for 0, 0.2, 0.4, all the way to 1. Now we could use a calculator for this, but a spreadsheet might save us even more time. So let's do that. Let's go to here. Let's open, let's just go to Sheets. Okay, oh, that's the wrong spreadsheet. New spreadsheet. No, back. Let's do this one. So, here. So here, let's move me here. I already did this to double check I could do it. Now let's go through and do it all again. Okay, so my step size is 0.2. I don't even need to do it like that. All right, and then differential equation is x plus x times y. Did that to remind myself. So then here I've got 0, 0.2, and then my spreadsheet can be kind of figure out where I am there. And so then let's move these columns around. Oops. Here, let's make this little y prime big. All right. So little y is equal to 2 times, and then e to the power, which in Excel or Google Sheets would be x. And then x squared, well, x is over there, squared divided by 2, and then minus 1. And then you go to that, where in the bottom right, it turns into a little plus sign. Pull that down. So those are my actual values. Okay, let's go back to here. What does it tell me to do? So it said compute y of x for those numbers. Use Euler's method to approximate solutions to the initial value problem for 0, 0.2, 0.4, all the way to 1. So here, y prime, I'm going to compute, well, I need y and then y prime. Okay, so here, y starts off with 1, and then y prime is equal to, it's equal to x plus x times y. So it's equal to x plus x times y. And then this value is equal to, so we're doing Euler's method, so it's equal to the last value plus h, which is 0.2, times y prime, which is this. So then this, I can drag that down. Let's see. Yep. So then if I drag both of these down, yes. So I've got, for clarity, let's just kind of not show as many zeros here. And we can kind of move them closer together. And so here I've got the actual values, and then here I've got my approximation values, which are based on these y primes that are calculated at particular times. So then my error is always equal to my, it's equal to this value, the value I think is there, minus the actual value. Oh. And so then here, you see that my approximated value, 1.9, is less than the actual value. So my error is negative to show that I'm below where I should be. Okay, so this is absolute error. And I could also do some relative error, just like they do in the book. So relative error. So that's equal to my error divided by the actual value. And then I want that as a percentage. So I'm off by negative 3.8% all the way down to negative 13.69%. Part of the reason it's not working so well is because my steps are too big. Euler's method works best with smaller steps. The smaller your steps, the closer it gets. So if I were to kind of make my steps like 0.01, it'd be much closer. Okay, now let's see. I'm going to pause the video here, but I can also graph this for you using Sage. So I'll pause the video now and I'll come back with a graph of it. Okay, here I am I'm working on a Sage worksheet, which you could do this inside any of those extra cells you're given in your textbook. But if you're interested in just working with Sage by itself, you could go to sagemath.org and you can download it onto your computer, or you can use CoCalc on the cloud. The cloud is super slow because of all the people who are using it, the free server to mine for Bitcoin. So if you aren't able to download it, the cells on your textbook actually work probably faster than this. But you're able to do many cells here, so whatever. But if you're able to download Sage, it might be useful. So here, I'm working in, if you download it, there's like 3 different versions, and I'm using Sage. I'm using Sage Notebook right there. And so the notebook lets me kind of do this thing. It's in a Jupyter notebook. And so I've written out some code that does the Euler method. It's a little bit, it's not very clean because I wrote it up so quickly. So I've started with the x min, or really the t min. The t min is 0, the t max is 1, h is 0.2. So the number of steps is max minus min divided by h. So the x values are, I'm just using some Python notation. So RR is Sage for make this thing a real number. So I is in the range num plus 1, and then it just gives you the numbers 0.0, 0.2, 0.4, 0.6, 0.8, 1. And then the y values are going to start off with the initial value there, just like it did in the spreadsheet. And then for each x value in these x values, y prime is, here's where my equation goes. So my equation is like y prime is x plus x times y. So x plus x times the last y value. So this is Python code for getting the last value of a list. And then y values that append, then the last y value plus h times y prime. So then you can see here I just generated the same numbers that I did in the spreadsheet. Now, I'm going to graph everything. So then x and y are variables of x, y. This is my differential equation. So then I'm going to plot the slope field here, and I'm going to solve RK4. So actually, that's the this is the last method we talk about in this section, actually. So this is, for real, a good numerical method. And so it finds the solution using the numerical method, the top-notch numerical method, and then we're going to plot our mediocre numerical method. So I'm plotting the points and then like kind of making little line segments in between them. And so then you can see that I'm getting further and further off from the actual solution because of how it kind of curves like that. And I'm using the Euler method, I get off because I'm too slow while curving, because I'm curving in jerks instead of continuously. And so each point here, it says each red dot, it looks at where am I in the slope field? Okay, and then it jumps there. And where am I in the slope field? Okay, it jumps there. And that's kind of what the Euler method does. So this is the end of this video.